ये रहा शेयर स्क्रीन, कहाँ है वो? ये रहा ना, फुल स्क्रीन है,
फुल स्क्रीन
शेयर। अभी कब करेंगे? मैं अभी शुरू हो जाता हूँ, 20 मिनट के बाद दे देना, और मोबाइल दे देना, अरे हम टाइम देख लें।
पाँच बज के 4 मिनट।
ठीक है,
बीच में आपको ग्लूकोज लाना है ना?
20 मिनट के बाद ग्लूकोज दे देना। ठीक है, अब मैं शुरू हो जाता हूँ। Good morning, everybody. So, first of all, I would like to thank the organizing committee to give me the opportunity for being keynote speaker in the 4th International Conference on Energy and Power Engineering, EPE 2021, September 17 to 18, 2021, organized at Guangzhou in China. And I am working as professor in Mechanical Engineering Department of National Institute of Technology, Silchar, Assam in India. So this is about presentation outline, and I will be talking on the recent advances in pulse detonation engines, and I will also be talking about what we have done, some work in our laboratory, and in fact we have not done any experimentation. We have done numerical simulation because here experimental facility on pulse detonation engine it is not available. So my presentation outline is introduction, literature review, objective of the present research, solution methodologies and physical model of pulse detonation engine, resultant discussion, and then publication out of this work. So this is introduction, that is pulse detonation engine. PD is a pulse or intermittent jet engine based on detonation combustion process. So 4 stages of PD are filling of fuel, air mixture, number 1, stage number 2 is combustion, then stage number 3 it is blow down, and stage number 4 is purging. Then out of the 4 processes, combustion is the most crucial one, since it produces reliable and repeatable detonation wave. And detonation is the more energetic process compared to deflagration mode of combustion process, which is essential to generate power or thrust. And PD utilize bulk products of high temperature and high pressure produced by detonation wave to achieve thrust. And this is different type of combustion process. That is stationary flame or propagating flame, then laminar or turbulent combustion, then steady or unsteady combustion, then single phase or multi-phase combustion, then homogeneous or heterogeneous combustion, then pre-mixed or non-pre-mixed combustion, then deflagration or detonation combustion. And this is deflagration and detonation combustion process. So this is the differences between these 2 processes, that deflagration. Here there are 2 types of flame, laminar flame and turbulent flame. And detonation, here detonation flame, and the velocity is more in detonation flame, that is 2000 meters per second, and pressure is 10 atmosphere. And for laminar flame, in deflagration, it is only 3 meters per second. So the next one, different type of detonation engine. So this is described here, that 3 types of detonation engines are there: pulse detonation engine, rotating detonation engine, and standing detonation engine. And present research area is pulse detonation engine and detonation combustion. So, and then another is rotating detonation engine, that is RD, then standing detonation engine, that is ST. So here we can see the PD operating condition, that is PD operating Mach number, and here we can see that up to what Mach number, what type of engine is coming into picture and to give best combustion efficiency. And then this is the air intake and fuel injection. This is combustion chamber and this is nozzle. So this diagram gives the description of pulse detonation engine. Then advantage of pulse detonation engine, that is, there are no moving parts in the engine, then high thermodynamic efficiency. Operating in a potential large Mach number range, that up to 5, simplicity and flexibility of geometrical configuration, then easy integration to vehicle and low cost. Then applications of pulse detonation engine. This is pulse detonation engine can be applied in turbojet combustion chamber, ground level application, the PD powered bicycle, go-kart, PD powered speedboat, then high mode application, that is PD powered supersonic flight, lifter rocket, and it can be applied for power generation. And this is literature review section, and in fact, many have experimented on this, and mostly in China, USA, Australia, other, then Germany also experimentation are done in the area of this pulse detonation engine. So it is better I should skip this part so that I can finish my topic in 30 to 35 minutes. So we have discussed here about literature review. So these all things I want to skip. Then these are the key issues drawn from literature review. That is, performance of PD depends on geometry of detonation tube. Then detonation initiation and acceleration in detonation tube using combustion wave flow path design. Detonation wave acceleration in detonation tube using different boundary conditions. Then PD efficiency depends on percentage of fuel in PD combustor. Then PD looks attractive for special missions, but it not yet totally mastered. Means much research is to be done in this area. Then objective of present research, this is influence of geometrical configuration of nozzle on propulsion performance of pulse detonation engine. Then to accelerate deflagration flame and transition to detonation wave. Then Selkin spiral can be appreciated in detonation tube for detonation wave enhancement technique. Then the detonation wave acceleration in detonation tube of pulse detonation engine combustor, the blockage configuration as an obstacle can be improved the detonation wave characteristics. And the exergetic efficiency analysis of hydrogen air detonation, pulse detonation engine combustor, then to have to provide computational simulation on initiation, propagation of hydrogen air detonation tubes with U-bands implying their use for design optimization of pulse detonation engines. The effect of ejector system on detonation wave propagation in pulse detonation engine combustor. Then solution methodology. So A is computational methodology, that is 3D geometry modeling, wave generation, then grid independent test for test meshing, we have done. Turbulence model selection for simulation, then specifying operating conditions as well as the boundary conditions. Then Dirichlet boundary conditions are considered. Then iteration should go on till the convergence criteria is fulfilled. And post-processing CFD result analysis, it is done and it is compared. Then numerical analysis. So we have got similarity with the CJ Chapman-Ducat theory behind the detonation wave speed, and then von Neumann and theory behind the detonation wave, and CFD result validation that we have done and that we have cited from literature. So physical model of pulse detonation engine chamber. Here it is given, and this is CD type nozzle, then C type nozzle, then D-type nozzle, then without nozzle also. So these are the things for physical model. So here 4 types of model they are given. Then physical model of Selkin spiral in detonation tube. So this is physical model of Selkin spiral, and this is sectional view of Selkin spiral inside the detonation tube, and this is Selkin spiral with divergent PDE geometry and photograph of experimental Selkin spiral. This work was done in 2009. And here, this figure gives blockage ratio, that is blockage ratio is equal to 1 minus small d by capital D whole square, where D and D denoted as workpiece and tube inner diameter. And this is PDE model of hydrogen air detonation combustor for XRG analysis. So this is very, very obvious from diagram. That is control volume for combustion thermodynamics in PDE combustor. This is exhaust. This is heat loss rate to surrounding. This is detonation tube. This is combustion chamber. And this is air, and this is fuel inlet. So, and this is physical model for PDE with U-bend geometry. So, and this is about experimental setup. So here, physical model of pulse detonation engine with exit ejectors. So here, geometrical parameters of the ejector, this is given. Then computational map generation for nozzle configuration. So we have done grid independent depth. So this is obvious. Then next one, map generation and mesh adaptation for Selkin spiral in detonation tube, and map generation and mesh application for obstacle configuration. Also, this is also self-explanatory. And this is map generation and mesh adaptation for ejector at exit of divergent pulse detonation engine. Then these we have done independent depth. Then this is numerical formulation, that this is formula for net engine thrust. Then the gross thrust is also calculated, then chamber wall thrust formula is also given. And this is mathematical formulation for XRG calculation. And this is numerical formulation for flame tip velocity and percentage difference calculation. And this is nozzle geometry effect on PDE thrust. So 4 types of cases are investigated. One is CD nozzle, that is convergent nozzle, convergent divergent nozzle, then convergent nozzle, then D nozzle, that is divergent nozzle, then without nozzle. So we have reached at the conclusion that at optimum Mach number of 1.4, the net 3449 Newton thrust was obtained in divergent nozzle configuration. So this diagram is given for Mach number 1.4. Effect on detonation wave dynamic pressure and velocity contour in different nozzle configuration. So all the 4 types of nozzle are explained here, and this diagram gives at Mach number 1.4. Then here also we reached up to conclusion that the detonation wave velocity contour plot clearly indicated that strong detonation wave accelerates in divergent nozzle configuration. The detonation wave is accelerated up to 1370 meters per second, that is m is equal to 4 in divergent nozzle geometry. And this is detonation wave velocity and dynamic pressure contour at Mach number 1.0. So this is self-explanatory figure, and this is we have studied at Mach number 1.6, and this is studied about Mach number 1.8. Then this is the story about divergent nozzle half angle and length effect on detonation wave velocity. So half angle, here we have 6 degree, 12 degree, 15 degree. Then three type of angle are given, 6 degree, 12 degree, and 15 degree. Then we reach up to the conclusion that from the correction factor point of view, 8 degree half angle is desired for increasing the moment of thrust. And this is result and discussion from Selkin spiral effect on detonation wave acceleration. So this is also self-explanatory. And this is also comparison of detonation wave for Mach number 1.35. And this is for comparison of other Mach number. So we can say that the detonation wave velocity and pressure 2500 meter per second and 25 into 10 to the power 5 Pascal are obtained at Mach number of 1.4, which is close to Chapman-Tucker detonation wave. So this is about contour plot analysis of Selkin spiral effect on detonation wave acceleration in detonation tube. So here we have done experimentation with large eddy simulation, LSE, then detached eddy simulation with realizable K-epsilon turbulence model, then detached eddy simulation with SST K omega turbulence model, that is ABC, and delta, that is blockage ratio 0.29, 0.49, 0.69, and 0.89. That we have used. And we have used this Fluent software for the purpose of analysis. So from the contour plot analysis among the three turbulence models, simulation among detonation wave was found using large LES turbulence model. That LES turbulence model, that is more realistic. And here we have seen validation of present CFD contour plots with experimental shadowgraphs. So this we have compared with the work done in 2013. And almost the results are similar. So we can say that our numerical results are in good agreement with the experimentation. And this is again a story about detonation wave dynamic pressure contour analysis in detonation tube with and without Selkin spiral. So here the variation is delta is equal to 0.39, then 0.44, then 0.49. Then delta is equal to 0.54, 0.59, and 0.69. So, and then again, delta is equal to 0.74, 0.79, and 0.84. So, with silicon spiral, we have done these simulations at Mach number of 1.35. So we can say that the peak detonation wave pressure was found from isosurface plane at delta is equal to 0.69 meter distance in detonation tube. And here also detonation wave velocity contour analysis in detonation tube with and without Selkin spiral. So this is given, this is with B is without Selkin spiral at M is equal to 1.35 and A is with Selkin spiral. So we can compare, you can see both the diagrams and compare. So here the main conclusion is the detonation wave velocity contour plot clearly shows that detonation wave gradually reach to CJ detonation wave with increasing the operating Mach number from 1.2 to 1.4. And this is again about the story about resultant discussion on detonation wave acceleration in obstacle-induced detonation tube. So, okay, so this is studied with blockage ratio and S is equal to spacing. We have done 1D, 2D, 3D. And blockage ratio, we have increased 0.4, 0.5, 0.6, and 0.7. And we have produced the numerical results. And we see that the smaller the obstacle spacing of S is equal to 1D and BR is equal to blockage ratio is equal to 0.4 is in good agreement with experimental wave velocity. That is our conclusion. And this is the story about percentage difference of detonation wave velocity in obstacle-induced detonation tube of pulp detonation engine. So here we can see that there are many conclusions, but the main conclusion is the blockage ratio 0.4 is desired for detonation wave velocity for 3 obstacle spacing. So this is temperature control plot validation in obstacle detonation tube. So this is the story about detonation wave pressure flow field contour analysis at different time steps. So this is detonation wave velocity contour plot analysis in obstacle landed PDE at operating Mach number of 1.359. And this is detonation wave velocity meter per second in the vicinity of the obstacle in detonation tube for blockage ratio 0.4 here. This is the analysis for blockage ratio 0.4. This is for blockage ratio 0.5. This is for blockage ratio 0.6 and this is for blockage ratio 0.7. And here we can say that the strong detonation wave velocities of 2270 meter per second, 2190 meter per second, and 1880 meter per second are found for 4 centimeter, 8 centimeter, and 12 centimeter obstacle spacing at different run-up distance. Then comparison of detonation wave properties in detonation tube with different obstacle configuration for operating Mach number 5. So this is also work done with numerical analysis. And we have seen that this is in good agreement with experimental results. So here we have seen that for comparison of spacing, S is equal to 1D, S is equal to 2D, and S is equal to 3D, the desired magnitude of detonation wave temperature, velocity, and pressure was found in S is equal to 1D. And the accelerating wave velocity eventually reaches to a value of 3200 meters per second, that is supersonic mode of combustion, and it is correlated to the CJ flame velocity in blockage ratio of 0.4. So we have reached up to maximum velocity 3200 meters per second. That is CJ velocity. And this is for S is equal to 1D. This analysis it is related with, that is supersonic contour plot analysis of detonation wave characteristics in supersonic flow condition for S is equal to 1D. Then we have seen here for all the blockage ratio, that is 0.4, 0.5, 0.6, and 0.7 at Mach number of 5 for spacing S is equal to 4 centimeter. So this is analyzed here. And here also this is analyzed for blockage ratio 0.4. So detonation wave temperature contour affected by obstacles. This is. So we have studied this, and for S is equal to 12 centimeter spacing at supersonic flow condition of Mach number 5, which is desirable for thermodynamic point of view. And the maximum temperature of detonation wave is here, 3185 degree Kelvin from S is equal to 4 centimeter obstacle spacing, and 3176 K from spacing S is equal to 8 centimeter, and maximum 3180 K temperature from S is equal to 12 centimeter. So then eddy viscosity contour of detonation wave affected by obstacles. Then this is the story about detonation wave velocity contour arrested by obstacles. So these results I want to skip because all our results we have got from numerical solution and simulation, and we have compared with experimental results, and we have observed that our simulation are in good agreement with experimental results. And in fact, from this work, we have got many research papers published in good journals on pulse detonation engines. So ultimately, I want to show the papers, and so here we can say that from the contour plot analysis, the desired detonation wave, dynamic pressure and velocity was found from 3.5 centimeter U-bend radius at the same operating conditions compared to other U-bend radius. And the maximum detonation wave velocity trapezoid area was found near the U-bend curvature for all three cases. So this is the story with U-bend and the Mach number at 4. Then this is static pressure contour analysis along the U-bend curvature. So we have done every type of possible analysis, and this is the photograph of PDE with ejector with firing, that is work done in 2007, that is experimental work. Then what I will come up to the conclusion means what ultimate conclusion we have done out of our work, that is concluding summary of our research work. That is the effect of nozzle geometry on thrust, dynamic pressure and detonation wave velocity are obtained from computational simulation at different Mach numbers to improve the propulsion performance of pulse detonation engine. And at optimum 1.4 Mach number, 3449 Newton third, was obtained in divergent nozzle configuration. Then thrust augmentation of divergent nozzle is better than convergent divergent nozzle. Convergent nozzle and without nozzle at whole operating conditions. And then the divergent half angle is responsible for increasing the correction factor as well as propulsion performance. And the contour plot analysis clearly shows that detonation wave are strong at 8 degree half angle. And this is conclusion drawn from Salkin spiral effect on detonation wave acceleration. So I have already discussed this previously. And this is conclusion drawn from effect of obstacle geometry on detonation wave. That is here what we have used. The blockage ratio we have used 0.4, 0.5, 0.6, 0.7. That is 4 blockage ratio we have used, and spacing S is equal to 1D, 2D, and 3D. 3 spacing we have used. And we have come to the conclusion that this blockage ratio 0.4 and S is equal to 1D, it is good comparatively to other combinations. And this is about conclusion drawn from exergy analysis of hydrogen air detonation. And this is conclusion drawn from effect of U-bend tube on detonation tube. That is, the important computational result finding is possible variation of the detonation wave after passing the U-bend and detonation wave transform to a marginal detonation wave with a CJ values. And these are the conclusion drawn from ejector effects on detonation wave. So we have done many type of numerical analysis, and the future research scope is also given, like in future it can be done, the investigation of detonation wave acceleration can be increased using orifice plates and multiple reflectors in detonation tube. Then heat transfer can be analyzed in detonation tube at different frequencies. Then internal groove effects on detonation wave characteristic can be analyzed. So then detonation wave can be simulated using multi-ejectors. So application of pulse detonation engines. So these are ground level applications. Then PD powered flight is there, PD powered lifter is there, PD powered rocket is also there. Then fully developed application is also shown here. Then these are the references. And out of that, we have got publication like in Journal of Combustion, that is Hindawi publication we published. Then SAGE publication also, that is one paper is published in International Journal of Spray and Combustion Dynamics. And other papers also we have got recently published, and it is not mentioned here. So this is also one paper we got published in Journal of Thermal Analysis and Calorimetry. The topic is numerical analysis of detonation combustion wave in pulse detonation combustor with modified ejector with gaseous and liquid fuel mixture. And then materials today proceedings also we got published. So we have got many publications out of this. And one paper is published in Journal of Applied Fluid Mechanics also in March 2017. So then we got some conferences paper also published out of this work. So ultimately, I am again very thankful to the committee for giving me the opportunity to be keynote speaker in this important symposium on power and energy. And I thank everybody for hearing patiently. And I will welcome all the questions by email, and I will be answering because I answer all the questions by mail. So once again, I thank everybody. Thank you very much. That is the end of the story.